Morning, Kyle. How are you? Good. Wife and kids all right? Anyway, moving along. We're in benzene. We're in the benzene chapter. This is a prelude to the big benzene chapter, right? This is the gentle run into the big benzene chapter. And we're talking about what should be on the exam next week, and I reckon I can get through a chunk of the next chapter in the time I have. So there's a lot of mechanism coming up. We've been away from mechanism for a while. There's a lot coming up. It's fairly intense stuff. So I would suggest that this weekend is important. Make sure you're happy with the material we have covered so far, so that next week you can talk about the next chapter, chapter 19, and be ready for next Friday. Now, we are talking about this structure that took a long time to solve, the idea that benzene isn't two equilibrating structures as shown by Kekulé at the top, in which the double bonds and the single bonds are shifting. That's not happening here. This was reconciled in the 20s by Robinson, who decided and brought in some more modern ideas of bonding, and showed that this actually is a resonance type situation, in which we can draw resonance structures like Kekulé structures at the bottom, but the actual pi cloud here is best represented like this. And you'll see this a lot as you read. Organic chemists tend to draw it as a Kekulé structure. You'll see why when we get there and we start pushing those electrons around, we need to have some bonds to work with. So this Robinson sextet is a nice shortcut. You'll see that often. And we need to wonder about why this thing is so stable. Benzene is not a simple alkene. It does not react with bromine under simple conditions. You've done this in the lab yourselves, where you added bromine to your alkene when you made it last semester, and you got rid of the color. And that tells you that it's reacting. Bromine doesn't do that. If you add bromine to benzene, it's not going to work. The color will be retained. So we have to worry about why. There are lots of experiments here to show that this is not a simple alkene. There's a nice chart here that shows you that benzene is way more stable than you expect relative to simple alkenes and to what we might call a theoretical triene. If you think about this molecule at the top, this is what we think, what people used to think benzene looked like, a triene. It doesn't work like that. It doesn't react. It's way more stable than that, and that's to do with conjugation. Okay? It's all to do with delocalization of electron density. So we have been building up these pictures. We've done this in recitation this week. We'll do it again today, of the bonding situation and anti-bonding situation, so that when we get to the aromatic stuff in more detail in the near future, we can draw these pictures with confidence and understand what is a stable system and what is not a stable system from the ground up. So with this in mind, there's a nice picture for benzene. It is completely delocalized. All the 6 carbons have 2 neighbors each. They're all in the same orientation. They're all sp2 hybridized. They all have p orbitals pointing in the same direction. They can all overlap. And so these are not localized bonds. This is even better than butadiene, where butadiene was overlapped in the middle, so you can delocalize across 4 atoms. Here you can delocalize across 6. Okay? Especially in a cycle, this is a great system, which will explain its stability. Again, we need to worry about these pictures. I do require you to understand them to the point where you can answer questions about them. In the past, I've often given you some empty orbitals, and you can color in the phases so that you can tell me whether it's a bonding situation or an anti-bonding situation. That's not too difficult. But the whole point of these things is, again, to understand where we start, which is 6 independent p orbitals now overlapping in a cycle. And you'll find when we draw something called a frost circle in a second, these things are actually quite easy to work out. You'll see now that we have 6 molecular orbitals because I start with 6 atomic orbitals. You have to retain that number. And we find now that we have a lowest energy system in which the electrons are all delocalized, and that's completely conjugated, and that's very much like the butadiene system. You put it next to that, it's very similar. And then we have 2 that have the same energy. We'll call them degenerate, because we have throughout, hopefully, from freshman chemistry. And at the top, we have a couple of degenerate antibonding orbitals. You can see the amount of overlap is starting to decrease. And if you think about the symmetry in the system, it should make sense that this is the same as this. You're just slicing the molecule in half from a different direction. And at the top, you've got the worst one of the lot, where there is no communication whatsoever. So it's the same idea with the nodes, right? You start off with 0, then you get 1, then you get 2, then you get 3. Same sort of idea from the beginning. What is of concern here is where are those orbitals relative to where we start, and what are populated? Which of these orbitals are populated, and that will help us work out whether this is a stable system or an unstable system. So when I deal with this, I have 6 electrons to populate these orbitals. I have pi 1, obviously, that goes first. We put 2 electrons in there, that's great. And when we put 1 in here, 1 in here, and then we go back and fill up, because degenerate orbitals fill up singly before they double up. But all 6 of those electrons go below where we started. Yes? So that's a very good system. That's a system in which all of those interactions are positive and bonding, and we don't have any concern about putting electrons back where we started or above that 0 line. So this is why benzene is so good. That's a starting point for today. If we understand that benzene is so good, we can go look at some other conjugated systems that look like they should also benefit from this aromaticity, this delocalization idea, but don't. They're actually unstable. Right? So that's a big deal for today. So keep an eye on that picture, be able to understand what the lines mean and what the arrows mean, and then be able to apply it. We're going to see systems like this. Cyclobutadiene, I think it's been made, but it's very, very unstable. And cyclooctatetraene is stable, but it does not benefit from the same type of resonance possibilities that benzene does. So something's going to come up here where you can actually calculate this. You'll have a little device called the Huckel rule to be able to work out, is a system aromatic, is it not aromatic, is it terrible? And that's something that you'll be tested on. So cyclobutadiene, to start off with on the left, it looks like it's got 4 pi electrons, it looks like it's conjugated. Why doesn't it benefit from this resonance stability? Why doesn't it benefit from the same factors that benzene does to make benzene so stable? And the answer is partly shape, and the answer is population of orbitals. We're going to see when we draw these pictures with the molecular orbitals, you put electrons in bad places. You can't put all the electrons in bonding orbitals, so therefore you get instability. So we'll start off thinking about these systems, some evidence for why they're not aromatic. If you think about the protons in a system in the NMR spectrum, where would a proton show in the proton spectrum? Where would an aromatic proton show? Where does AR8 show in the NMR spectrum? Let's say 7 or 8. Let's say 7 or 8, right? Where do alkenes show? 4 or 5. There's a definite difference, right? If you put benzene in the spectrometer, you see signals at 7. If you put the cyclooctatetraene in the NMR spectrometer, you see signals at 5, right? That's telling you it's an alkene. Now, characteristically, if it's an alkene, it should do the same thing simple alkenes did last semester. For example, at the top, this reaction with bromine. Where benzene does not react with bromine under simple uncatalyzed conditions, cyclooctatetraene does. This system now will pick up bromine, and the answer is because it's not as stabilized as benzene, and it's more reactive. So in this case, we get the typical addition across the double bond in a trans or anti-fashion, and that gives you the colorless outcome, and that tells you you've got a reaction. So this thing here is reacting as if it's an alkene, not as if it were a stable system like benzene. This is marvelous. I'm not going to worry about this in terms of you getting it or understanding it, but it's what happens to cyclobutadiene. If you can make it, it dimerizes. It's so reactive, it reacts with another molecule of itself, and you get this intermediate species, which then opens up and gives you, in fact, cyclooctatetraene. So that's just an indication that these things are way more reactive than benzene itself, and there has to be some explanation for that. So what we'll start doing very quickly is talking about Huckel, German chemist, who came up with this observation that certain systems with a certain number of electrons in a cycle were able to be stabilized by aromaticity, where others were not. Others were unstable. So this is the beginning. This is fairly straightforward, but people can get confused on this. The first thing you need to worry about is how many pairs of pi electrons. In this case, I've got 2 pairs, so how many total electrons in the pi system? 4, right? So when I write this down, that's what that means. 4 pi system, 4 pi. Whereas with the benzene, I have 3 pi bonds, and so this is a 6 pi system. On the right-hand side, 4 pi bonds, 8 pi. Okay? Now, that's the first thing you need to do to apply Huckel's rule. And Huckel's rule at the bottom, you can see here, is something about delocalization, it's something about shape, it's something about orientation, whether the molecule is flat or not, and also how many electrons do you have. And when you plug it into this equation, what's the outcome? Is the outcome a whole number, or is the outcome a fraction? It turns out if the outcome is a whole number, the system has aromaticity, right? They're not related in terms of, it's not because it's a whole number it's aromatic, it's just a test. It's a little device to help you work out, and it's consistent. So at the bottom, you can see that the number of pi electrons is equated to 4n plus 2. So in the system at the top, if I equate, let's say start with benzene, my system here would be 6 pi electrons equals 4n plus 2. So what does n come out to be? 1, right? So n equals 1. So that test, as part of the rule, is okay. It's a whole number. It turns out that benzene is aromatic. Now the second component here, the second thing that you must remember for Huckel's rule is that the system has to be flat. And there's a very simple reason why it has to be flat. If it isn't flat, you can't do all of that conjugation. If it isn't flat, that's not necessarily sp2 or it's twisted, and so the p orbitals cannot communicate if it's not flat. So the system overall has to be flat. So Huckel's rule basically is, does your system fit this rule where n equals a whole number, and is the system flat? If both of those criteria are fulfilled, the system tends to be aromatic. It's a nice little test to be able to do this. So to start off, I'll do a couple of examples. If you think about the 4 pi system on the other side, I've got cyclobutadiene. We've already said that its chemistry exhibits, it's way more reactive than you might expect. And in this case, we've got to think about 4n, or 4 pi, equals 4n plus 2. That's all you do. You equate one to the other, and then you work out what n. So what's n here? Half. Okay? That, you'll see in a second, is not aromatic. It doesn't fit the rule. And we'll see why when we put the electrons in orbitals, why it's not aromatic, in fact, why it's so unstable. It's fairly straightforward. If I go ahead and do that again, if I do that with a cyclooctatetraene system where 8 is the number, 4n plus 2 equals 8, what does n come out to be? 3 over 2? Yep, certainly it's not a whole number. So n here is 3 over 2, and that then again is not aromatic. So Huckel's rule is something you should know. I've seen it on, again, standardized tests, so be aware of how to do that and how to use it. So there's a basis to this. There's a reason why these systems are not stable where benzene is. And it's fairly straightforward when you look at the possibilities for the overlaps. There is a picture of the conjugated pi system in cyclobutadiene. And yes, you have 2 pi bonds next to each other, and they all have neighbors. They all have 2 neighbors, so it's similar to benzene, but for some reason, this is terrible. It's just not as stable at all. Well, the answer comes about when you draw the molecular orbital diagram. And we'll have a little device in a second called a Frost circle that allows you to draw this for any of the cycles you need to be concerned about. In this example, we find out that the 0 point, where you start out as p orbitals, right here, if you draw this setup, this picture, you find that you get a bonding molecular orbital at the bottom, as you usually do, very stable system, and then you go higher. And that going higher usually involves a node. And that node, in this case, unfortunately, the energy of those orbitals happens to be at the same place that we started out as p orbitals. Okay? If you're putting an electron into a p orbital, then it's not as stable as it could be in terms of it being a bond. So we'll refer to these as non-bonding molecular orbitals, simply because they're not communicating with anything. Now, if you put 4 of these things together, 1 pi, 2 non-bonding, and 1 pi star, you have to put the electrons in there. And you have to go all the way back to high school or freshman chemistry and worry about what is the order of putting electrons into orbitals. I can only put 2 into any orbital, right? And I fill them up singly before they double up. If you're talking about what we call degenerate orbitals, like p orbitals, you fill them up singly before they double up. So if that is followed, this is fine at the bottom, but what's the problem here? What does this look like? What type of species does that look like? It looks like a radical. And this is even worse, right? This is a diradical where 2 electrons seem to be split into 2 orbitals. So the basis for the instability of cyclobutadiene is not necessarily its shape, but it's to do with the population of the orbitals. You have to put electrons into non-bonding orbitals, which can be fine if they're paired up, because what's a non-bonding orbital that's paired up? It's a lone pair, yeah? But in this case, no, they're split. And if they're split, it's a super reactive diradical, and that explains its reactivity and lack of stability. So that works for cyclobutadiene. That's fairly straightforward. If we go to cyclooctatetraene and we try to draw out its pi system, you can see again, it's drawn in that picture as a flat, planar system. All the p orbitals have 2 neighbors, and so maybe they should be able to communicate. But it turns out that this doesn't happen. Okay? This molecule is not flat. It's actually sort of bent, and it's actually unstable or reactive. Now again, if we work out the orbital picture, and again there's a device coming up to be able to do this, you find that the population here, this is fine, I've got 8 electrons, I've got 8 orbitals, I fill them up singly before I double up, but when you get to here, the energy of these orbitals is exactly the same as a p orbital. It hasn't bonded to anything. And if you populate those orbitals, you have to fill them up singly before you double up, and in this case again, one has to go here and one has to go there. That looks like a diradical. That looks like an unstable system. And to avoid this possibility, this molecule actually will bend. It will pucker, and it will give you this sort of bent shape like this that gets rid of some of these possibilities because it's unstable, and it reacts like an alkene because the pi bonds are not talking to each other. So you've got to be careful. 4 pi? No. 6 pi? Yes. 8 pi? No. 10 pi? What do you reckon? Yes. Right? So there are some systems that you'll see a lot of. You see this in biology with porphyrins. You see this with aromatic systems like porphyrins in heme and in chlorophyll and things like that. These rules do actually work. You can actually use them. So the question you should be asking is, how on earth do I draw these pictures? Where do these pictures come from? Well, a lot of it's mathematically based, but we can actually use a device to construct them yourselves. And I'd be happy if you could do up to about a 7-membered ring. I think an 8-membered ring is kind of tricky, but you can do it. And this is something called a frost circle. Again, this is a device to help us handle the information. And Frost came up with this idea that if you construct one of these circles and you put in the shape that you're trying to work with into this frost circle in a certain way, it turns out that all the corners of these shapes match the orbitals in terms of the molecular orbitals. So what does that mean? It means if you start out with a circle, and if you can't draw a good circle, don't worry about it. I don't even bother with the circle anymore. You just have to be able to draw the geometric shapes. So we can see here the circle, and then the next thing to do is to take the cycle that you're dealing with, in this case a 7-membered ring, and to set this up so that the bottom, or one of these corners here, is touching the bottom of the circle. It then turns out that there's a pretty good estimation here that each of these points where it touches the circle matches the pattern for the molecular orbitals of that particular system. It's nice, it works really well. So you practice it with 4, you'll see it's pretty straightforward. Then do 5, then do 6, it becomes quite straightforward. And in that case, you don't need to necessarily draw this again because you've already got it here. You start to populate. And if we're starting in terms of energy, we're going to populate down here first, and then here, and then here, and then we might double up before we have to go above. So this is a useful thing to be able to do, and I will expect you to be able to draw these things. So what we've got at the bottom is this picture for cyclobutadiene. I'll draw that one. We'll also see some systems in which we have 5-membered rings that can be aromatic or not, and 6-membered rings, definitely. Benzene is certainly aromatic, and this is consistent because you can see now, just looking at these pictures, I'm going to have to populate here, and I'm going to have to populate here, not necessarily here. I'm not going to have to do it there, but I may have to do it later on. I may have to do it there, and I might have to do it there, and then I might have to do it here, and I might have to do it there. Okay? So if you can do this frost circle thing, you've got a good chance of being able to understand why some things are reactive and why some things are stabilized. Okay? Right. So let's have a go at drawing one. I can't draw circles. I'm rubbish at drawing circles. So I know the rule says put one of the points at the bottom. So I'm going to draw a square to try and show the shape of cyclobutadiene. So the system I'm trying to work out here to see if this thing works is this with 2 pi bonds and 4 pi electrons. So I tip my square over onto its end, and I put this thing at the bottom, and then I draw the horizontals. And those horizontals are the orbitals that I'm dealing with. And you can see it's symmetrical, and then you have to put electrons in. So I have to put 4 electrons in here. Fair enough. 2 will go down there, no problem. There's a decent bonding molecular orbital. But next I've got to put 1 here, and because I've got to fill up singly before I double up, I have to put the next one there. That's the picture for cyclobutadiene that we just developed. All right? So have a go. It's not particularly difficult. We'll practice it in recitation this week and next week, and be ready for it. Yeah, if you can draw a circle, great. I'm not particularly good at that. I don't know what that is. I don't know. Isn't being able to draw a circle a sign of madness or something? Or genius? I certainly can't do that. All right, so practice it and have a go. Now, once you've got those frost circles constructed, we can start to talk about systems that don't look an awful lot like the simple ones that we just dealt with. In this example here, we're looking at some problems and some unusual looking molecules that might be aromatic. At the top left, not aromatic. Why not? Because it's not a cycle. You have to have complete communication around a cycle to be able to be aromatic, to be able to benefit from this idea. So in this system here, why not? There is a break in the communication. Okay, just like the isolated dienes, if we put a break in the communication, you can't possibly delocalize around the whole thing, and so that thing is not going to be aromatic. And then some systems just try, they do their best to be stable, and in this case, the cyclooctatetraene bends or puckers to become this sort of shape to avoid having to put electrons in bad orbitals, and the shape isn't there. So these are things that lead to systems that will not be aromatic. You must have a cycle, it must be completely conjugated, and it must be flat. And then you work out how many electrons are involved, where they go, and you'll see it fits. So down here, we've got systems here which are flat. Believe it or not, this is flat. Believe it or not, this is flat. And when you progress to biochem, you'll see the one on the bottom right is very important as a basis for porphyrins and holding metals in space for various biochemical processes. And they're all aromatic. Okay? Now, you may be, you'd have to be told maybe that the one on the right is flat, but the other two are fairly obvious. They're going to be flat. And at the left, we fit in Huckel's rule, 4m plus 2 equals pi. Here, n equals 1. How many pi electrons here? 10, so n equals 2. Yeah? So that's going to fit. And how many electrons over there? How many pi electrons? 14. 7 pi bonds, 14 pi electrons, so N is a whole number. They're all aromatic. They're all aromatic. If you take the NMR spectra of these things, the protons will show around 7 for the same reason they did in the benzene ring. So it's consistent. So what you've got now is a reasonable idea of what Huckel's rule is and how to apply it when you see a system that is unfamiliar to you, and also maybe drawing frost circles so you can work out the reasoning behind some of these ideas. Anybody? Casey, all right? You look cold. Yeah? It's going to be 32 on Saturday, apparently. I can't wait. Right, here are some weird ones. Here are some ones that you can get tripped up on quite easily if you're not careful. This is a 5-membered ring. Now, how can a 5-membered ring be aromatic if we're dealing with 6-electron systems? Well, you can do that if you put extra electrons in there. So we have a classic system here, and I'll start out at the bottom. It turns out that a classic CH bond, as far as you know, has a pK of what? What was a CH bond so far? 50, 60, right? The top end. It's not acidic at all. But this material at the bottom, cyclopentadiene, has a pK of 16. Now, what else do you know has a pK of 16? Water, alcohols, right? They're moderately acidic. So there's something about this molecule that's quite different that makes it a pretty acidic carbon-based molecule. And the answer is, when you take off that proton and you make the conjugate base is aromatic. And so we have to understand that. So in this example, we'll see that if we drew the frost circle, we have 6 electrons. Where do I get 6 electrons from? 2 from the pi, 2 from the pi, 2 from the lone pair. Where does the lone pair come from? Take off that proton, there's a negative charge. That's 2 electrons. So total here I've got 6. 2 from there, 2 from there, 2 from there. This is called pi excessive in the sense that you've got more electrons than atoms. So this is a decent nucleophile, it's a decent base, but it is stabilized by resonance because it is completely conjugated, it is delocalized, it is flat, and it has the right number of electrons. And if you want to work on that, if you want to populate this thing at the top, 2 of them go here, fair enough. 2 of them single before you double up, but I've got 6 total. That looks an awful lot like benzene. That looks an awful lot like the picture for benzene. The number of orbitals is different because you have 5 atoms instead of 6, but that's the same picture for benzene. Everything's below the 0 point, everything's in stable bonding molecular orbitals, and that's a decent molecule. Michael? Yes. Well, it's a salt. Now, it's a salt, so it's going to be a little bit difficult in the NMR spectrum, right? But you could estimate that they would be down there around 7. Yeah. Yes, it would. It would stop it reacting in the Diels-Alder because it's no longer 4+2, right? It's now a 6 pi system. So we're explaining phenomena here. This is a remarkably acidic carbon-based acid that you haven't seen much of yet. Everything we dealt with so far contains pretty much pKa's up in the 50s and 60s. That will change after the break when we get into more biological stuff, but so far everything's been quite high. So you explain the acidity of this molecule by the fact that the conjugate base is stabilized by resonance, and you can draw all these resonance structures, of course, but this has this added component of being aromatic. It's a 6 pi system spread out over 5 atoms, and it can be aromatic. So if you were to draw this thing in reality, we see this quite a lot. If you take inorganic chemistry in the future, you'll see this, where this is drawn with a Robinson sextet like that, and it's got a negative charge. Okay? Cyclopentadiene anion. Yes, it's aromatic. Next one. This looks different. This looks weird. You have 7 atoms in a cycloheptatriene type system. 7 atoms with a positive charge. Now, what is that positive charge? What shape is that carbon if it's a positive charge? sp2. So it's an empty p orbital. A positive charge was always an empty p orbital. So in this example, you have 7 orbitals, but with 6 electrons. So this will be pi deficient. But you can still benefit from aromaticity and spreading the electron density around here because of the fact that it is flat, it is conjugated, and everything's pointing in the same direction. So if you want to draw the resonance structures, great, there are many of them. Okay? It helps explain the stability of the system. But if you want to put the electrons in, how many do we have? 6, right? Nothing in the p orbital, but you've got 6 from the pi bonds. And so I would put 2 here, I'd put 2 here, and I'd put 2 there. And again, that looks a lot like benzene. In terms of where the orbitals have been populated and in terms of their relative stabilities, everything's below the 0 point. Everything contributes to bonding. So you'll see a bunch of these. There's a lot of good practice out there, website, Wiley Plus, whatever, all kinds of good stuff to practice these things and be confident with it. And this is something that does show up in the future. Many of you have to take these standardized tests. This is often on there from the organic component. Okay, anybody got anything to say about that? You can do this with small cycles, big cycles, and you can work out quite nicely whether it should be good or bad. So we have this property now of aromaticity. Aromaticity really is helping stabilize things. Michael? Bicyclic compounds you can work out, but you usually do it individual cycles to make sure they're individually aromatic. Yeah. Susan, you all right? Now, heterocycles. Anybody with an interest in medicine or pharmacy or forensics or anything like that, you have to be happy with heterocycles. Heterocycles are happy, right? These are compounds that are ubiquitous. They're in many, many different natural products. They're very important in terms of medicinal chemistry. So this is a classic problem. If you understand this problem, I think you understand aromaticity. We have two systems. Pyridine on the left is a 6-membered ring. Pyrrole on the right is a 5-membered ring. The one on the left has a lone pair. And the lone pair on the left goes right there. The nitrogen on the right, if it needs 8 electrons, has a lone pair. The lone pair goes there. Can we see those at the back? Little dots. Okay? These two molecules have quite remarkably different properties. This one is basic. This one is not. How so? Well, they've both got lone pairs. You need a lone pair to be a base. Both of them have lone pairs, but only one of them is basic. There's something about the lone pair and the pyrrole on the right that does not allow it to be used as a base. If you look on the system on the left, I've got 2 pi electrons here, 2 pi electrons there, and 2 pi electrons there. Within the cycle, I have the full complement of 6 electrons to make an aromatic system. In other words, I don't need this lone pair. That lone pair is not needed to make up the aromatic sextet. So this molecule has a lone pair that's available. It's actually pointing at 90 degrees away from, you can see the picture at the bottom, it's pointing away from the cycle. It's not part of that pi system at all, and that can be basic just like anything else can be basic. However, on the right, I've only got 1 pi electron, set of pi electrons there, 1 set of pi electrons there, that's 4. So in order to get 6 in the system, I need that lone pair. So now, it is a 6 pi system, it is stabilized by resonance, but only if you use the nitrogen's lone pair. So it's not now sticking out of the cycle, it's actually part of the pi system, it is stuck in that aromatic sextet, and you can't use it as a lone pair. And you can see that on this next slide. Okay? At the top, we've seen pyridine do this. We've seen pyridine. When we did tosylations last semester, where we tosylated an alcohol to make it a good leaving group, we used pyridine as a base. And it does exactly that. If you employ the lone pair here to go after an acid, the product is still aromatic. You don't lose any of this extra stability. If you do that with pyrrole, no, not a good thing. In fact, a bad thing. If you look at this, that's a 6 pi system with the lone pair. If you want to draw a picture with the orbitals, right there. You can see here that that p orbital is necessary, and the lone pair within it is necessary to actually be part of the 6 pi system. If you choose to use that as a base, you get over here, and that becomes a 4 pi system. And it's a 4 pi system that's only slightly conjugated. It certainly is not aromatic. Mr. Homan. Pyrrole itself actually has a reasonable pKa. It's probably a little bit less than you're used to. You're used to about 38. It's probably lower than that. All right, because we're talking about sp2 carbons, which grab electron density better. Yeah, so you can take that proton off. But the whole point of this, and something that I think you ought to be happy with to understand and make sure you understand aromaticity, the top system you can use as a base, the bottom system you cannot, simply because of the lone pair and where it is and where it's needed. At the top it isn't needed for the pi system, at the bottom it is. Exactly. Remarkable, isn't it? Okay. Right, just some bits and pieces, then we'll get into some chemistry. In this chapter, we just sort of lay out what aromaticity means. We look for some tests to be able to make sure we can tell whether the system is aromatic or not. And we give you some examples. Now, you can build these things bigger and bigger. I mean, there are molecules out there which have 10, 20, 30 benzene rings in them. They're huge systems. And a lot of these are the combustion products of things like coal. They're not particularly good for you. Naphthalene, naphthalene we use a lot in terms of things like mothballs. Anthracene is a cool compound because it kind of fluoresces under a TLC light. It's not very good for you. And likewise, phenanthrene at the bottom. They're pretty nasty compounds. And the reason is they get into your, if you ingest them, they get to your liver, they get oxidized to epoxides, and the epoxides get chewed up by DNA, and they can actually alkylate your DNA, and that's a really bad sort of carcinogenic system. So these things are dangerous, but they are aromatic. And again, each of those cycles, if you worked it out, has 6 pi electrons, and they would be aromatic. So there's some examples of those. What I really want to get into today is discussion of the chemistry from this chapter, so that I can get into 19. 19, I think, is heavy. In 18, you might write this down. 18, the chemistry you're going to see is primarily outside the cycle. It's primarily at what we call the benzylic position. Now, you know this from the past, benzylic from the NMR spectroscopy, stuff like that. We've defined what a benzylic position is. It is directly outside a 6-membered benzene ring. So if I were to look at this system, here, this is not benzylic, this is not benzylic. They're simple primary. Here, definitely. Here, definitely. Now, if I were to put a positive charge on this carbon, so far it looks like a primary carbon, but it's much better than that. It isn't a simple primary carbon anymore. It's a benzylic carbon. And what will a positive charge benefit from at that position? Resonance. From the cycle, we'll be able to borrow those electrons, spread the electron density out, and you will see significant stability at the benzylic position, be it a positive charge or a radical. So what we'll do for the rest of this chapter is really talk about chemistry at those 2 positions. So if you're not good at resonance, you need to be so quickly so we can understand these things. Chapter 19, you'll get systems with 5, 6, 7, 8, 9, 10 resonance structures that are possible. Be happy with the localization. So we'll start off with a reaction that is very useful, it's very powerful, but nobody seems to know how it works. And I often do this, I usually do this every year. If you can come up with a mechanism for this that makes sense, I will give you an A straight away. Now bear in mind, the rest of the planet has not been able to do this yet. Okay? If you can come up with this mechanism and experimentally prove it, you can get into the textbooks. Okay? Nobody's done it yet. So what's happening here is an oxidation event. And at the top, we find that benzene itself is very difficult to oxidize because it's so stable. And it does not have any benzylic carbons. So these molecules tend not to react with very powerful reagents that you've seen before, like sodium dichromate or potassium permanganate. Highly reactive oxidants don't touch benzene itself. But you start to do this with benzene with an alkyl group, we can get things to work. Now, just to prove how important the benzylic system is, this slide is showing you here, no reaction. Here, no reaction. Alkanes don't work. You put the 2 together, all of a sudden, you've got a very, very useful access to benzoic acid and carboxylic acids on a benzene system, and they're very useful. So something's happening here that involves the breaking of the bonds at this position. And thinking about a mechanism, it has to involve something here, maybe a radical, maybe a positive charge, nobody knows for sure, that is stabilized, okay? That isn't present in the 2 molecules above it. So these are called benzylic oxidations. This is something that you don't need to worry about the mechanism for this, but it is very powerful. Any benzylic position will be oxidized as long as it has at least 1 hydrogen. That's something that you need to write down, okay? This molecule at the top, T-butylbenzene, does not react. Now this should make some sense. If you're doing an oxidation, what are you removing? You're removing hydrogens. If you don't have hydrogens, you can't remove them. So it's somewhat like the tertiary alcohols. The tertiary alcohols did not get oxidized because there was no proton there's no hydrogen on the carbon being oxidized. If you have the same system here, it doesn't work, it's consistent. So we can see now that a T-butyl group won't go, but any alkyl group other than that, isopropyl, long butyl chain, you make this chain as long as you want, it will oxidize. Now a little modification down here. This one tends to give the salt, which you can protonate, but overall they give the same outcome. You break this molecule, we don't really care what happens to that other piece, it gets destroyed, and you end up with this carbon being oxidized to the carboxylic acid. So there's lots of possibilities for that, and there are some examples out there. If I try to draw this one as an example, we'll do more of these in recitation, but if you were to take a system like this, benzene ring, and then something like that system, this is a classic problem to make sure you know what you're doing. Oxidize that. Use that with something like permanganate or sodium dichromate. And it has 2 benzylic positions, 1 here and 1 here. They both get oxidized. And so what you end up with, very nicely, is a molecule that has all kinds of use in polymer chemistry, which is this dicarboxylic acid. You end up with a carboxylic acid right there, and a carboxylic acid right there. And the other carbon probably went away as carbon dioxide, but we're interested in this piece. Again, any benzylic position other than a tertiary position will oxidize like this. That's useful. So there's one reaction that we talk about, but we haven't got a mechanism for it. And now we can start talking about some that we do know mechanisms for. Free radical halogenation. It's been a while. But you need to go back and remember what's happening here. You need to remember about the formation of radicals. You need to remember about single arrows being pushed. And you've got to worry about selectivity. Now, which is more reactive, or which is more selective, bromine or chlorine? Bromine. Don't get that mixed up with other brominations. This is a radical reaction. The bromine radical is more stable because it's less electronegative, it's bigger, it's more selective, so it shops around. In this case, you'll get exclusive halogenation at the benzylic position, nowhere else, because that's the best radical you can form. Once you take that hydrogen off, and again, we've already done this, I'm not going to repeat it. That hydrogen comes off, you put the radical here, it's stabilized by resonance. You put the radical elsewhere, it is not. So therefore, that's a very good system. Other things you can do, and you know the mechanisms here also, you can think about SN1 reactions. This is an SN1 reaction in which the solvent is involved. What was that called? Solvolysis. And solvolysis will be very important to you in biochemistry, so be happy with it. SN1s all over the place in biochem. So what's happening here is that the leaving group is breaking off. And again, bromine's good at leaving, so make it leave. Take it off. In this case, it's an ionic process in which you get a carbocation. And these are pictures we've drawn before, but you should be okay. You can delocalize over that whole system. And this will lead to an interesting intermediate, because the intermediate will have some positive charge here, some positive charge there. We could write delta positive on each of these carbons. But look at the exclusive product. You get all of that. Why don't you get any product in which water attacks here? Or water attacks there? Why is that not formed? The most stable system you can get is the top system. Okay? The answer really is the fact that the only molecule that retains the benzene ring is the one that's shown. If you attack any of these other carbons, you lose the benzene ring. You lose that extra stability. And that becomes much more important in the next chapter when we start using those electrons in the cycle. So we have three systems now. We can do oxidations, we can do halogenations, and we can do hydrolysis, if you like. Lots of possibilities based on things you have seen. Now, this is a dangerous couple of slides because this is the stuff you have seen. I'm not going to repeat it. You need to go back and practice it. Make sure you're okay, because these will be useful for synthesis. Other things we can do, again, there's a lot of chemistry on that slide from 3719. If you made flashcards, or you've got my mechanism videos out there, go back and look at these things, refresh yourself, and make sure that you're okay. In this system, SN2, good nucleophile, maybe some polar aprotic solvent like BMF, and we're attacking a primary carbon. Now, it's a primary carbon that's a bit different because it's benzylic, but that cycle, let's think about this in terms of transition states. Do you think this cycle is a problem? It looks like it's big. Do you think it's a problem in the SN2? John, you're shaking your head and because it's not. Why do you think it's not a problem? It's flat. That cycle's flat, so it doesn't really matter. It doesn't get in the way. So SN2s are fine at this position. In fact, they're enhanced. They're faster. So benzylic SN2s are great to produce things like this. In this example, E1. What sort of intermediate are we dealing with E1? Carbocation. So same idea as the previous slide. Protonate this thing, break it off, put a positive charge right here, and away we go. And again, the conditions are conducive to E1, not SN1, because of the fact that we have a non-nucleophilic acid or counter conjugate base. Down at the bottom, how do you know this is E2 and not E1? Oh, it's been a while. Strong base, right? The strong base is so reactive, it will not sit around and wait for that molecule to collapse. So the carbocation won't get formed. This thing will go after one of these protons at the beta position, and it will do a very fast process like this. It's concerted. It was one step in a reaction profile, and it will give you the elimination. So again, Zaitsev applies all that sort of stuff. In this case, you don't have much choice, and you can get an alkene. So keep an eye on that. There's weekend stuff for you. It's going to snow all weekend again, so stay inside. In terms of what we just talked about, there's a nice little slide to review. That summarizes it. Halogenation, substitution reactions, oxidation reactions, radical halogenations and eliminations. And guess what? Next week there'll be synthesis on there. There'll be a whole bunch of steps in which you have to give me products, and now we've got a lot more chemistry to deal with. It's the same stuff as previously, but it's including the benzene ring. And when we get to 19 and we can do chemistry on the benzene ring, oh boy, it just opens up. All right, okay, now, some examples here of things that are useful if you need to do this. There's a mechanism coming up that I'm going to not have you learn, but this is something that is an indication of how stable benzene really is. If you look at the molecule at the top, the actual aromatic system, and you treat this with hydrogen gas, you really have to work at it. It needs a catalyst, and it needs very high pressure and quite high temperature. But you can get rid of those pi bonds. Okay? There's a definite penalty to pay because you're losing the aromatic character, but it can work. At the bottom, look at this. Under normal conditions, normal I say we can do in the lab pretty easily, the benzene ring and the pi bond. Only the pi bond goes. And that should be sort of intuitive by now. The pi bond is somewhat stabilized by resonance and delocalization, but this is certainly aromatic and this is kind of added onto it. And so we can get rid of that pi bond by doing regular hydrogenation. And always there was no mechanism for that, right? There was never a sort of a detailed mechanism for how that works. Well, this one is a bit different. I'm going to do it. I'm going to show the mechanism. I'm going to ask you. I'll tell you, don't worry about repeating this mechanism. Okay? It's a reaction that looks particularly horrible to run. You take benzene and sodium, methanol, and ammonia, and you reduce. You get rid of one of the pi bonds. You end up with a diene. And it's difficult to do. You need sodium metal. The sodium metal, think about what it will bring. It will bring an electron to the game. This material here will bring a proton to the game. And the hydrogens that have been added here and at the bottom will add in certain places depending upon what's on the benzene ring. So in the simple system, it's fine. You just get that diene. Will that diene do a Diels-Alder? No, it's not conjugated. They're not next to each other. It has to be next to each other for this to work. So the reaction happens down here. You can see a fairly complex setup in which we've got the benzene itself accepting an electron. It's a sodium metal. You put an electron into the system, you make it unstable. You know, it's somewhat similar to the mass spec stuff we did. You make the system unstable by putting either too many electrons in or bumping an electron out. And if we do that at the bottom, we get something called a radical anion. And that radical anion, the anion part of it needs a proton. So we go pick up a proton. That's where one of the protons gets picked up. You can cover this in the intermediate organic class if you take that, if you're interested in that later. That leaves us a radical. That radical needs another electron. There's more sodium around. The sodium donates an electron, you make a second anion. That second anion gets protonated from the solvent, you're finished. So this is called a Birch reduction, and it's very useful. It's kind of dangerous to run, but it works. And it allows you to selectively get rid of the benzene ring and end up with a diene. In terms of some of the things that you ought to be happy with, you're swapping sp2 for sp3. You're going from something that had less hydrogen to something that had more hydrogen. And you ought to be happy, and I'll do this now mainly because it's coming up in the next chapter. Depending upon what one that R group is, you get different outcomes. And this is nothing more complicated than, does that R group stabilize a negative charge or destabilize a negative charge? And this is foreshadowing what's coming next week and Friday. What do you think? If you put an R group on there that's electron withdrawing, does that stabilize a negative charge or destabilize a negative charge? Stabilize, of course it does. And you put something on there that's electron donating, it destabilizes a negative charge. So if you look at that mechanism, I get rid of all the noise, I want to have here something that will stabilize the negative charge next to it. That's the basis of the regioselectivity that you'll see in a second. So if I put something here that's electron donating, it will destabilize a charge right there, and that charge will go someplace else. If you put an R group on there that is electron withdrawing, it will stabilize, and so you'd want the negative charge next to it. That is a huge amount of the next chapter. So here we go. In the R group here, in this case, if the R group is electron donating, the pi bonds go in a certain orientation. That's because if you were to put a negative charge here in the mechanism, that R group, which is electron donating, is destabilizing it, so the charge is elsewhere. If you put something on there that's electron withdrawing, look at this. If you put that ketone on there, you get the opposite outcome. In the previous example, double bonds went here. In this example, double bonds go there. all to do with where you want to put that negative charge for a rationale, for why that happens. What you need to be concerned with is, in this system, R is donating. That system that's the outcome. In this case, R is electron withdrawing. That's the outcome. And then, of course, you have pi bonds now. You can do all sorts of chemistry with those products. On the right-hand side, at the bottom, fairly complicated system, but you ought to be able to recognize this as electron withdrawing. If that's the case, the pi bonds end up here. Nothing more complicated than that. So know that one, so we can use the products. Anybody? Is anybody still out there? 78 people left out of the 140 we started with. Oh boy. Michael. Were the fluorine over here? Maybe, maybe not. Maybe it's too far away. You know, it dies off further away. Maybe. Cassandra? How's Cody doing? Is he all right? Yeah. Don't make him talk. He won't shut up. Okay. So there's the birch reduction. I'm not sure that word was on there, so we need to make sure that word is on there. Birch. Okay. Very useful way of getting rid of benzene ring. Miss Nye. Then it's great fun because you probably get mixtures. That's beyond sort of the scope of what we're interested in there. Yeah. No, probably not. No, probably not. Okay. Spectroscopy. We always throw this in now to make sure we keep up with this stuff. Alkenes have their own unique bands, and aromatics have their own unique bands. And I want to point out maybe, again, on the infrared spectroscopy sheet, which will be page 15 of your exam next week, and you're welcome to rip it off and use it during the exam, then you'll notice that at the bottom right of the spectroscopy sheet is a whole bunch of bands related to aromatics. Okay, monosubstituted, disubstituted, and all that, whether it's ortho, met, or para. Those should make some sense now. Go and look at those and make sure you're comfortable with it, right? So here we see, you know, there's a IR spectrum of typical sort of benzene systems. You've got the typical sp2ch type thing over here, carbon-carbon pi bonds, if you will, in the 1500, 1600 region, and then indicative symbols down there. But again, next week, you will have proton, and you'll have carbon, and you'll have IR, and you'll be able to put it all together. So those pieces of information will just be to help you work things out and finesse the answer. In terms of NMR spectroscopy, again, we hammered this stuff. We've done a lot of this in recitation. I think most people are comfortable with it now. Looking at 7. That's one of the first things you do when trying to work out a product. What is the molecule? Look at 7. If there's nothing at 7, it's probably not aromatic. It's probably not a benzene ring. If there is something at 7, away we go. Look at the C13 spectrum. If you look at a molecule like this, how many signals in the aromatic region for this molecule in the C13 spectrum? It's symmetrical, so how many signals? It's symmetrical along this axis here, but not along that one there. So how many signals in the C13 spectrum? Kyle sees 3. Anybody, any advance on 3? 4. That's logical, isn't it? That comes next. I see 1 here. I see 1 here. These are the same. These are the same. I think that's 4 signals. And what characteristic will you see for the 2 signals in the middle? They'll be identical, sure, but how does that show on the C13 spectrum? They're higher, double intensity, right? They're higher in terms of being on the spectrum. So there's a clue as to things like symmetry. So we've done a lot of this stuff. We can now apply it to benzene chemistry. It's much more useful. In the C13 spectrum here, again, practicing these problems, working out what the structure is from an unknown. Look at the C13 and count the number of signals. If you have fewer signals than carbons in your molecule, it's symmetrical. If you have very few signals, it's very symmetrical. If you have the same number of carbon signals in your C13 spectrum as you were given the number of carbons, there's no symmetry. They are useful clues to be able to work things out. And there's some useful patterns, which we did talk about previously, to help you do these problems. Now, I'm going to stop there. And then, when I get here on Friday, we are into chapter 19. So do yourself a favor, keep up.